Introduction to Binary Trees. So welcome everyone. Today we're going to look into a fundamental data structure, which is a tree. So it has root, branches, and leaves. And in computer science, trees are similar but inverted. So they will start with a root at the top and branch out downward. And each point is called a node, and the connections are edges. A unique path connects to each pair of nodes, ensuring no cycles. And this makes the structure hierarchical and nonlinear. So understanding trees is important in understanding more complex data structures and algorithms. So moving on, for this lecture, we are going to focus on a specific type of tree, which is the binary tree. So in a binary tree, each node can have at most two children, often referred to as the left and right child. This constraint introduces a simple yet powerful structure that underlies many systems and algorithms, from file systems to databases. So the beauty of binary trees lies in their recursive nature, which means every subtree is a binary tree in its own right, offering elegant solutions to complex problems. Types of binary trees. So a full binary tree has nodes with either two or no children, creating a balanced appearance. You'll be able to see an example here. We see that root has two children, and level 1 has also two children, and level 2, we have the outermost nodes have two children, but innermost nodes have zero children. And complete binary tree, what happens is it ensures that all levels are fully filled, except possibly the last, which is filled left to right, optimizing spaces. So what happened here in the example is when we fill trees, we would fill from the left to right. So in level 2, left one is filled, the next one, and the next one. And then if we have another node that we're going to add, then it will come right in the level 2 rightmost node. And we can talk about the perfect binary tree. It means that every interior node has two children and all leaves are at the same depth, representing an ideal structure. Lastly, a balanced binary tree minimizes height to ensure operations like insertion, deletion, and search are efficient. So it is important for real-world applications. Representation of binary trees. So each node in a binary tree contains the three essential parts: the data or value, and a pointer to the left child and a pointer to the right child. And this structure is mirrored in memory, where each node is dynamically allocated and pointers stitched together the tree, enabling the traversal and manipulation of its structure. So we showed in the beginning how the tree node would look like. In a tree node class, we have constructor to store value, and there will be pointer to left child and pointer to right child. So we can assign tree node to root, and then in the root left, we can assign another tree node, and the root right, we can assign another tree node as well. Now let's move on to traversal methods. So to work with binary trees, we need to traverse them or visit each node systematically. There are 4 ways to do this: pre-order, in-order, post-order, and level order traversal. So let's look at pre-order first. What happens is we would start at the root, then we would explore the left subtree and right subtree recursively. So if we look at this pre-order, the numbers are assigned in the order of this traversal method visits the node. So we would visit the root first as 1, then we would go to left subtree 2, and then we would in the left subtree we would visit root and then left subtree. And in number 3, since we visit root, we try to visit left subtree, but left subtree does not exist, which means we will visit right subtree, and since 3 is leaf node, there is nothing there. So we finish visiting left subtree. Then we will visit right subtree of node 2, which is 4. And when we get to 4, we will try to visit left subtree and right subtree, and nothing's there. So we will go all the way back up, and we've explored this entire left subtree here, which means uh, we will visit the right subtree. So we will visit this right subtree 5, node 5 last. And then since there's no left subtree and right subtree for node 5, our traversal ends. For in-order traversal, what happens is we traverse the left subtree first, then visit the root, and finally the right subtree. And this method is particularly useful in binary search trees for retrieving sorted data. So we will start from here. We will, instead of visiting root, we will visit left, and then we see that there's left exist here. So we will first go to here, and then we'll try to visit left subtree of this node, but left subtree does not exist. So we would hit root, and then we would hit right subtree doesn't exist. So since we explored this area, now we go back to root, and then we'll check right subtree and then left subtree. And in this right subtree, we will try to hit left subtree first, then root, then right subtree. Then we have visited this entire left subtree. So we will go to this node root, then we'll go to right subtree, and then we'll try to visit left subtree and get root, and then right subtree. Similarly, post order, you visit unlike in order, you will visit left subtree, right subtree, and root. So you go all the way left to the left subtree, and then instead of going to root first, you go to right subtree, and then root. Then you will go to right subtree, then root. And level order is when you visit nodes level by level, starting from the root, which is great for breadth first searches. So you'll visit first the root, and then 2, 3, then 4, 5. Application of binary trees. So binary trees are more than theoretical construct. They have practical application in computer science. Um, Binary search tree is an example. It allows you to efficiently search and sort, and this is a lot of times a foundation for databases and search algorithm. And heaps are specialized trees that is used for priority queues and sorting algorithms. And syntax trees are used in compilers and interpreter to parse and execute programming languages. Huffman coding trees is another example. Is used for compression algorithms, minimizing file sizes without losing data. Binary tree operations. Working with binary trees involve three fundamental operations. Insertion, which is adding a new node while maintaining the tree's property, especially in binary search trees where the order is crucial. Deletion is removing a node, which can be complex as we need to reorganize a tree to fill the gap without breaking its rules. Searching, finding a node's value. Uh, this can efficiently be executed in binary search tree thanks to their order structure where each decision um, have the search space. So we're going to look at practical examples. So three things: constructing a binary tree, and also traversing, and we'll visualize how tree structure and traversal path works. So here is an example of constructing a binary tree, which you saw in the slide in the beginning. So you can create a tree node that contains value and pointer to left subtree and pointer to right subtree node. And traversal method, we saw pre-order, in order, post order. So if we are to use recursion, we can just print for pre-order, print, and call pre-order again, so that um, this pre-order happens for left subtree and right subtree. For in order, you would uh, recurse to left subtree first, then print, then recurse to right subtree. For post order, you recurse to left subtree and right subtree, then print. And here is an example of binary tree traversals again. So feel free to take a look at this and see how each order of traversal is different. Conclusion: to wrap up, binary trees are a really important data structure since it offers a blend of simplicity and efficiency, and they form the backbone of many systems and algorithms, proving their worth in diverse applications from software systems to data processing. So understanding binary trees paves the way to mastering more complex data structures and algorithms, expanding your toolkit as a software developer.